In the previous video, my dear students, we looked at expression for pressure volume work. In that we got this expression, the expression that I'm highlighting, that is W is equal to minus PEX delta V. In that, pressure was kept constant. Now let's take a look at expression for maximum work in which pressure is variable. That means it may vary. It is not going to be kept constant. Let's see what expression do we get when we vary pressure. So from the previous expression for work, what we got was W is equal to minus Px delta V, right? Now, for small changes, we can write this same equation in this form. dW is equal to minus Px dV. Now, what is this dW and dV? When small changes take place in work and volume, I can replace that W with dW and I can replace this delta V with dV. Now, volume with dV. Now, P minus Px, okay, that is pressure, and pressure when it is expanded, that is the change in pressure. I'm calling it as dP, okay? Or in other words, I can just rearrange this equation like this: P expansion is equal to capital P minus dP. Now capital P is that initial pressure, which is there initially. Now P expansion is when the gas is expanded. That time whatever the pressure is, it's called as Px, okay, that is Ex. So when I replace this equation in this is what we get. So dW is equal to minus P minus dP dV. All I've done is this Px is replaced by P minus dP, okay, from here. Okay, so when I open the brackets, I get minus P dV plus, so minus into minus becomes plus, so plus dP dV. Now here, my dear students, this dP dV is a very small value which can be ignored, which can be neglected. So that's why I've written here, neglecting dP dV, since it is a very small value, we get dW. This dW has come as it is over here, minus P dV. Why? Because the second half, the second part, I'm ignoring it, I'm neglecting it because it's a very small value. It's just like saying 0.00001. Can I approximately take it as 0 because it's a small quantity, right? Okay, so dW is equal to minus P dV. Now suppose if I integrate it. Now in maths, you must have studied this chapter on integration. Integrating both the sides, I get this value. The symbol of integration is what I put. So dW is equal to minus integration P dV. Now integration of dW is nothing but W max. That is maximum work. What are we doing? Expression for maximum work. No? So W max is equal to minus. So the limits are what? From V1 to V2. Okay, so from V1 to V2, those are the limits that are applied for this integration P dV. What do I get? For ideal gas equation, what do I know? Remember we did this equation PV is equal to nRT last year. Okay, ideal gas equation. If I replace that in this equation, that is P dV, what do I get? So I can only exchange or replace this P. How? That PV nRT, I make it as P is equal to nRT upon V. Okay, PV is equal to nRT upon V, or P is equal to nRT upon V. So I get W max is equal to minus, then I have this V2 with V1, from V1 to V2. So nRT upon dV by V. Okay, so here what I get is, there should have been dV upon V. So when I send the notes, I will just add that. So dV upon V. Now nRT, my dear students, is a constant term, and if you've done integration, you'll agree with me. Whatever is constant, it comes to the left of that integration sign, and whatever is on the right hand side of the integration, that's where you apply integration, okay, or the formula of integration. So nRT, I keep it there, and dV upon V, I keep it for integration. What is dV upon V, or 1 upon V dV? Log V, isn't it? That's the formula. So minus nRT to natural log, that is ln, or log to the base e, we get V. Which are the limits here? So we were at this last equation. So W max is equal to minus nRT log to the base E. The other way of writing log to the base E is ln. Remember, we always take log to the base 10. We'll come to that in some time from now. But when we remove this integration value by applying the formula, so we get dv upon vs log to the base E, or natural log of v, and limits are v1 to v2. Okay. Now, when I apply log to the base 10, when I convert natural log into log to the base 10, I add this factor of 2.303. This factor is added to log to the base 10. So W max now becomes, so instead of minus nRT ln V, V1 to V2, what now I get is minus 2.303 nRT log to the base 10 V2 upon V1. Okay, now why do I get that? Because log to the base 10, when I apply to V, it actually comes what? Log V2 minus log V1. I'll repeat. So this is V2. So log V2 minus log V1, that's what I'll get. But when you apply the formula of logs, what is log A minus log B? Log A upon B, isn't it? So that's how I get here log to the base 10 V2 upon V1. Okay. Now, if you remember Boyle's law, okay, last year, what does Boyle's law say? P1 V1 is equal to P2 V2, or P1 upon V1 is equal to P2 upon V2. No? So that's what we have looked at. So P1 upon P2 is equal to V1 upon V2. That was the formula. So it's written here. Or we could easily say P1 V1 is equal to P2 V2. No? So instead of V2 upon V1, can I write down P1 upon P2? Yes, I can, because that's what Boyle's law has stated. No? So this equation, W max is equal to minus 2.303 nRT log to the base 10 V2 upon V1 can also be written like this. W max, that is maximum work, is equal to minus 2.303 nRT log to the base 10 P1 upon P2. These two equations, my dear students, they are very, 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 very important equations. Okay, so if at all a question comes in the exam, derive the expression for maximum work, and the bracket, if it's written pressure variable, this is what you need to derive. Or straight away they'll ask you like this: derive W max is equal to minus 2.303 nRT log to the base 10 P1 upon P2. If they give you that, then you'll have to start with all this that you see here. No, so with all this you'll have to mention, and then you'll get full marks for deriving this equation or this equation. This is V2 upon V1, this is P1 upon P2. From where do I get that? From Boyle's law. Okay, let's move on to the first law of thermodynamics. There are different laws of thermodynamics, my dear students. There's first law, second law, and third law. We'll look at first law of thermodynamics. It is related to conservation of energy. Remember, we know what conservation of energy says. Energy can neither be created nor it can be destroyed, but it can be transferred from one form to another. Okay, you must uh, have recollected when I just stated this sentence. So that's conservation of energy. No, so but energy can be transformed, from one form to another. Yes, it cannot be created nor it can be destroyed, but from one form to another, it can be transformed. Now, what does the first law of thermodynamics say? The total energy of a system and its surroundings remains constant when the system changes from the initial state to final state. No? For example, if I keep one ice bar, a solid ice, and that is my system, I keep it on the table. Over a period of time, what will happen is that ice bar, from a solid, it will turn into liquid. Why? Because ice melts, isn't it? No? So which means my system, which is my ice bar, from the initial state of solid, in the final state it's become liquid. Okay, but the total energy of the system and the surrounding remains constant. How does it remain constant? We'll look in some time. So when we talk about first law of thermodynamics, it is related with conservation of energy. I was just talking about it a few seconds ago. So when the system changes from the initial state to final state, as in the case of ice bar, okay, what remains constant is total energy of the system and the surrounding. Remember, if the ice is melting, it just means that it's losing its energy to the surrounding. No, it's just like saying if your friend has got 0 rupees, as in if he has nothing in his pocket and you've got 10 rupees, suppose if you give him 10 rupees, no, so what will be the total that both of you would be having? 10 rupees. Isn't it? Initially it was 10 because the 10 rupees was with you. And if you give the 10 rupees to your friend, still what will be the total? 10. So it remains constant. That's the meaning of how system and surroundings work. So there is an exchange of heat from system to surrounding and from surrounding to system. So in the end, what remains constant is the total energy. Now, let's take a look at a new term called as internal energy. Every substance has its internal energy, an energy which is associated with that substance, okay, which is a definite amount of energy. So every substance is associated with definite amount of energy. This energy stored in a substance, what is it called? Internal energy, and it is denoted by capital U. Now, internal energy is never a single quantity. It is always in the form of its difference between the final state and initial state. Okay, so if the initial state is, suppose for example, for instance, if I say 10 and final is 20, so what will be the internal energy? Delta U will be 20 minus 10, which is 10. Okay, so never it is something that is an individual quantity, it will always be a difference. Okay, how do I write down the mathematical equation of internal energy? Delta U is equal to Q plus W, where Q is heat and W is work. So what is delta U? It is increase in internal energy. No? So for small changes, if the change is very, very small, I make it as du is equal to dq plus dw. Okay, those are for small changes. So you'll always deal with internal energy in this form, that is delta U, increase in internal energy or change in internal energy. Now take a look at first law of thermodynamics for various processes. Now there are different processes. Which are those? There is isothermal process, there is adiabatic process, there is isochoric process, and there is isobaric process. Now all these terms must be new for you. We'll just take a look at all the processes one by one. So when I say isothermal process, what do I mean? I mean it's a process when the temperature is constant. Okay. When I say adiabatic process, what do I mean? I mean there is no exchange of heat taking place. No exchange of heat. That is adiabatic process. What about isochoric process? So there volume is kept constant, and in isobaric process pressure is kept constant. So when I look at this equation, which equation am I talking about? I'm talking about this equation. Delta U is equal to Q plus W. Depending on whichever process I am in, accordingly that equation will change. Suppose if I say constant temperature, that is isothermal process, automatically internal energy will be zero. If I keep the temperature constant, that means there would not be changes in the temperature, changes in energy. So delta U becomes zero. So my delta U is equal to Q plus W becomes what? Zero is equal to Q plus W, isn't it? So if zero becomes Q plus 0 is equal to Q plus W, or Q plus W becomes 0, can I write down Q is equal to minus W? I can. Or can I write down W is equal to minus Q? Definitely I can. So in isothermal process, the delta U is equal to Q plus W becomes Q is equal to minus W. What about adiabatic process? Wherein there is no exchange of heat, that means Q will be 0. Remember what I told you, Q is what? Nothing but heat. But if the exchange of heat itself is 0, Q will be 0. So delta U is equal to 0 plus W. So I can clearly write down delta U is equal to W. This happens when no exchange of heat takes place or during an adiabatic process. In isochoric process, constant volume. Now you would say, sir, delta U is equal to Q plus W. There is no volume here. But if you remember, what is W? W is minus P delta V, which we got for expression for work. no, at pressure constant. So so isochoric process basically has volume constant, okay, which means internal energy, which is the sum of heat and work, that is heat is Q and work done is W. But since work is the product of pressure and delta V with a negative sign, okay, since we are talking about isochoric process, which means it has constant volume. So constant volume means the final volume and the initial volume would be same. So if both are same, what will be the difference? Delta V. So it will be equal to 0. No? So W is equal to minus P delta V, which I already know. And if I put it in this equation here, delta U is equal to Q plus W, what will happen is I'll get delta U is equal to Q minus P delta V. But since delta V is 0, this entire factor here, the term here becomes 0. Therefore, during an isochoric process, the internal energy or the change in internal energy is equal to the heat. Therefore, we say delta U is equal to Q. And finally, isobaric process. Isobaric process means pressure is kept constant. Okay. Now, for example, this equation here. Okay, so I'm picking up this equation from here. Delta U is equal to Q minus P delta V. And instead of writing Q, I write it down as QP. That QP, it just means that I'm talking about a condition at constant pressure. Okay, so heat at constant pressure. So what will be the heat? Okay, so let me rearrange this equation. So QP becomes delta U plus P delta V. So in all these cases, my dear students, okay, be it isothermal process, adiabatic process, isochoric process, or isobaric process, we looked at how heat can be found out, okay, using the equation of internal energy as a reference point. Okay, so isothermal process would be W is equal to minus Q. Adiabatic process, delta U is equal to W. In isochoric process, it will be delta U is equal to Q. In isobaric process, it will be QP is equal to delta U plus P delta V. Let's take a look at second law of thermodynamics. We have already done first law of thermodynamics. Now we will go to second law of thermodynamics. The statement of second law of thermodynamics is total entropy of a system and its surroundings increases in a spontaneous process. Okay, now that's the statement. Now in this statement, you'll find a new word, entropy. Okay, so what does this mean? The meaning of entropy means randomness or disorderliness. Okay, there are some more statements of second law of thermodynamics which we'll do it gradually. But since I picked up the first statement, so I'll explain that to you. Now, entropy of a gas is higher than entropy of a liquid. Entropy of a liquid is higher than entropy of a solid. Now, what do I mean by this? It just means that gas, it is highly in that disorder state. Now, for example, if I just keep an incense stick at the corner of a room, it will just keep moving everywhere. You know, the gas keeps moving, so it is highly disorderly in nature. When it comes to liquid, it is slightly lesser. Okay, suppose if I just pour water, after pouring, I do not know where the water will go. So suppose if I'm trying to pour water on the floor, no, so that depending on the smoothness of the floor, the water will just move around here and there. Okay, whereas in solid, we know that it is, as compared to liquid and gas, it is more orderly in nature. Okay, so basically entropy is a thermodynamic function and it is denoted by letter S. Okay, so S is the symbol of entropy. Okay, it is nothing but measure of the degree of randomness of a system. Greater the randomness of a system, larger is the entropy. Okay. Now, why did I speak about entropy in detail? Because in the second law of thermodynamic statement, you'll find total entropy.